In a galaxy billions of light years away, a star 100 times more massive than the Sun is meeting its end. In a brief, brilliant flash, it will radiate more energy than 1 trillion suns combined, sending tremors across the very fabric of space-time. Tonight, our journey takes us through cosmic phenomena so extreme they reshape reality itself. We shall witness explosions that outshine their host galaxies, visit black holes that consume light, and examine the elementary forces that bind the universe together. Brace yourselves for a voyage into power that defies imagination. Our exploration starts now. A silent, invisible war is fought deep within every atom of your being. In the nucleus, protons are crammed so tightly that their mutual positive charges should force them apart with incredible violence, much like trying to force the same poles of two powerful magnets to touch. And yet, they are held fast by the most potent force known to exist. The strong nuclear force asserts its absolute authority over distances tinier than a single proton. Physicists have measured its strength to be 100 times greater than electromagnetism and a staggering number of times more powerful than gravity. To put it in perspective, if gravity were a mere whisper, the strong force would be a deafening thunderclap capable of shattering mountains. This power is mediated by particles known as gluons, which serve as unseen tethers binding quarks into the protons and neutrons of atomic nuclei. The more one attempts to separate these constituent particles, the mightier the force becomes, akin to stretching an elastic band that only grows thicker and more resilient the further it is pulled. This peculiar characteristic, known as confinement, makes it impossible to ever isolate a quark, regardless of the energy applied. Within every proton, 3 quarks are trapped in a perpetual dance inside a prison of pure force. The gluons that hold them are themselves carriers of the strong force, weaving a web of interactions so intricate that our most advanced supercomputers find it difficult to simulate. When you attempt to pull quarks apart, the energy you pour into the system simply materializes as new quarks and gluons. It is like trying to cut a chain only to find new links forming in its place. The strong force reigns over scales so minuscule that a femtometer, 1/4,000,000th of a meter, feels like a vast expanse. In this realm, the familiar rules of classical physics collapse entirely. Space and time themselves become indeterminate, wavering according to the bizarre principles of quantum mechanics. This fundamental interaction governs the very architecture of matter, dictating which atomic nuclei are stable and which are not. It establishes the burning rate of stars and maintains the delicate equilibrium between creation and annihilation at the heart of every sun across the cosmos. Without the strong nuclear force, the electromagnetic repulsion between protons would cause them to fly apart instantly. The formation of atomic nuclei would be impossible. Nuclear fusion within stellar cores would never ignite. The universe would be a simple expanse of hydrogen atoms and unbound electrons. But for all its magnificent power, the strong force possesses a crucial limitation. Its influence extends only to the edge of an atomic nucleus, a distance about 100 trillionth the diameter of a human hair. Beyond this microscopic domain, other forces assume command. Now, let us journey into the wider cosmos, where distance is paramount, and observe the spectacle that unfolds when gravity and light clash in the most ferocious detonations ever recorded. Somewhere in the universe, a concentrated beam of energy slices through space at nearly the velocity of light. For a mere 10 seconds, it unleashes more power than our sun will generate over its entire 10 billion-year lifespan. This event is a gamma-ray burst, the most powerful explosion the universe can muster. These celestial behemoths are born when the most massive stars in creation collapse into black holes. We are speaking of stellar giants that contain the mass of 20 to 100 suns, consuming their nuclear fuel at a pace that would deplete our sun in a few million years. Once these giants exhaust the fuel for their fusion reactions, gravity emerges as the undisputed victor. As the star's core implodes, it ejects jets of matter and energy from its poles at 99% of light speed. The collapsing heart gives birth to a new black hole, encircled by a disk of superheated material. Magnetic fields, twisted and magnified by the collapse, function like cosmic cannons, launching these jets with extraordinary precision. The jets tear through the dying star like a projectile through soft tissue, emerging as focused beams of ruin that stay tightly aligned over immense distances. Imagine a laser beam that could maintain its focus on a journey from Earth to the nearest star. These jets achieve a similar feat on a scale millions of times greater. A lone gamma ray burst can momentarily outshine a trillion stars. If human eyes could perceive gamma rays, these explosions would appear more brilliant than the full moon, even for galaxies billions of light years away. The energy discharged in seconds surpasses what 10 trillion hydrogen bombs could produce if they detonated every second since the beginning of the universe. The most potent gamma ray burst ever observed, nicknamed the Boat 4 brightest of all time, took place in October 2022. It was so powerful it overwhelmed gamma ray instruments throughout the solar system and caused measurable disturbances in Earth's upper atmosphere from 2 billion light years away. Imagine standing on Earth and seeing a flashlight on Alpha Centauri appear as bright as an automobile's headlight. That gives a sense of the impossible power of these events. The light we see has traveled for eons, carrying news of stellar demise from a time when the cosmos was young and its stars were more massive and violent than any we witness today. Astronomers have identified bursts so far away that their light embarked on its journey when the first stars were forming, less than 1 billion years after the Big Bang. These ancient signals offer us a window into the early universe, a time when massive stars lived brief, violent lives, enriching space with the heavy elements needed for subsequent generations of stars and planets. Yet, compared to the entities that hide in the darkness between galaxies, even these colossal events seem insignificant. At the center of our own Milky Way resides a monster 4 million times more massive than the Sun. This object, Sagittarius A*, consumes anything that strays too close, from vast clouds of gas to entire stellar systems. This titan, however, is considered modest when compared to the true giants of the cosmic ocean. Some supermassive black holes harbor the mass of 40 billion suns, all compressed into an area smaller than our solar system. They are cosmic voids with gravity so powerful that nothing, not even light, can escape once it crosses their event horizon. Space-time bends around them like water spiraling down a drain, producing distortions that would seem unbelievable if we did not have direct observational evidence. These gravitational leviathans did not grow gradually. The most distant quasars shine from an era when the universe was less than 1 billion years old, fueled by black holes that somehow swelled to billions of solar masses in what amounts to a cosmic blink of an eye. How they managed such incredible growth remains one of the greatest puzzles in astronomy, as conventional stellar evolution fails to account for their existence. The prevailing hypothesis suggests these giants originated as massive seeds formed directly from collapsing gas clouds in the early cosmos. Unlike stellar mass black holes born from dying stars, these primordial monsters might have possessed hundreds of thousands of solar masses from their very inception, giving them a crucial head start to grow rapidly by feasting on nearby matter and merging with other black holes. As gas spirals into a supermassive black hole, it is heated by friction to millions of degrees, forming an accretion disk that can glow brighter than 100 billion stars. This disk spins so fast that material near its inner edge moves at a substantial fraction of light speed, undergoing time dilation effects that would make seconds stretch into hours for a distant observer. The most brilliant quasars, fed by these consuming black holes, are visible from across the observable universe, acting as cosmic lighthouses that broadcast their existence over billions of light years. They outshine their entire host galaxies, making the combined light of hundreds of billions of stars seem faint in comparison. The most ferocious black holes expel jets of particles at nearly light speed, forming beams that can extend for hundreds of thousands of light years. These jets carry sufficient energy to reshape entire galaxies, heating gas clouds to millions of degrees and suppressing star formation across vast swaths of space. The jets can stay active for millions of years, continuously injecting energy into their surroundings. Recent studies have uncovered black holes that appear far too large for their host galaxies, defying the usual relationship between a central black hole's mass and the properties of its galaxy. These oversized behemoths challenge our models of how galaxies and their central black holes co-evolve. But even these titans are subject to forces that operate on unimaginable scales. Across the 138 billion light-years of observable space, an unseen influence is winning a cosmic tug-of-war. Every second, it drives galaxies further from one another, stretching the very substance of space-time. This enigmatic power, known as dark energy, constitutes 70% of all that exists, yet we understand almost nothing about its true nature. Dark energy behaves unlike any other force. It doesn't diminish with distance as gravity and electromagnetism do. Instead, as the universe expands, more dark energy seems to emerge to occupy the newly created space. The larger the universe gets, the faster it expands. It is a cosmic accelerator pedal that is perpetually pressed down, growing more potent as it shoves everything apart. Scientists stumbled upon this force in the 1990s while observing distant supernovae, expecting to find that the universe's expansion was decelerating due to the gravitational attraction of all its matter. What they discovered was the complete opposite. Space is expanding more rapidly today than it was billions of years ago, as if an invisible agent is pulling the cosmos apart with increasing vigor. Picture the universe as a balloon being inflated by an unseen breath. Dark energy is that breath, causing every point on the balloon's surface to recede from every other. Galaxies are like vessels on this expanding ocean, powerless against the current that carries them into the cosmic abyss. The total amount of dark energy increases as space itself grows, seemingly contradicting the law of conservation of energy, one of physics' most sacred tenets. Yet, observations consistently confirm that the energy density of dark energy stays constant even as the volume of space increases. The origin of this additional energy is a complete mystery. Some theories propose that dark energy is an intrinsic property of space, a kind of cosmological constant that Einstein first theorized and then dismissed as his greatest mistake. Others speculate it might be a dynamic field that evolves over time, or perhaps evidence that our theory of gravity requires significant modification on the largest scales. The implications of dark energy are both profound and chilling. In the distant future, it will rip apart everything we can see. First, galaxy clusters will be pulled beyond one another's sight, becoming isolated islands in a sea of expanding void. Then, individual galaxies will find themselves unable to hold together against the relentless expansion. Eventually, even atoms might be torn asunder in a scenario physicists have dubbed the Big Rip. Stars will be extinguished, planets will be cast away from their suns, and ultimately, the fundamental particles of matter will be separated by immense gulfs of nothingness. Dark energy, which appears so gentle today, will become the universe's final executioner, undoing everything that gravity and the other forces spent billions of years assembling. Imagine compressing a mountain down to the size of a sugar cube. The resulting object would still be 1,000 times less dense than a neutron star. These cosmic relics pack the mass of our sun into a sphere just 12 miles wide, generating gravitational fields so powerful they bend light and warp space-time into incredible configurations. But gravity is not their most formidable feature. Neutron stars wield magnetic fields 1 trillion times stronger than Earth's. These invisible force fields ensnare charged particles, accelerating them to nearly the speed of light and creating beams of radiation that sweep through space like cosmic lighthouses. The magnetic field of a typical neutron star is so strong it could wipe every credit card on the planet from a distance of 400 miles. If one could approach within 1,000 kilometers, the magnetic pull would be sufficient to extract the iron from your bloodstream. The field lines themselves become visible as they trap and funnel streams of charged particles into focused beams. When these magnetized neutron stars rotate, they become pulsars, emitting jets of radio waves and X-rays with the regularity of an atomic clock. Some spin over 600 times per second, faster than a household blender, yet maintain a rhythm that rivals our most precise time-keeping instruments. Each pulse signals another rotation of a stellar corpse spinning in the void. The surface of a neutron star is a domain of impossible physics where familiar matter cannot survive. The magnetic field is so immense it stretches atoms into needle-like filaments aligned with the field lines. Normal atomic structure is completely dismantled, replaced by exotic states of matter found nowhere else. Any ordinary substance falling onto a neutron star surface would be instantly flattened into a layer mere millimeters thick. The gravity is so crushing that a marshmallow dropped from a few feet would impact with the force of a hydrogen bomb, releasing more energy than all the explosives detonated in World War II. Some neutron stars, known as magnetars, possess magnetic fields 1,000 times stronger still, nearing the maximum intensity permitted by physical law. When these objects undergo starquakes, their crusts fracture and shift, unleashing more energy in 1/10 of a second than our sun emits in 100,000 years. These magnetic cataclysms produce giant flares detectable from across the galaxy. The most powerful magnetar flare ever seen temporarily disrupted Earth's upper atmosphere from a distance of 50,000 light-years, showcasing the extraordinary influence of these stellar remnants. The magnetic field surrounding a magnetar is so powerful, alters the vacuum of space itself, making it birefringent like a crystal. Light waves become polarized as they traverse this magnetized void, offering astronomers direct proof of field strengths far beyond anything achievable in Earth-based laboratories. But these stellar relics are merely the beginning of nature's most bizarre creations. Stretching across the observable universe may be invisible threads that could slice through planets like a wire through butter. These cosmic superstrings, if they are real, are one-dimensional phenomena thinner than a proton, but potentially longer than entire clusters of galaxies. They are theorized to be scars left over from the birth of the cosmos, marking phase transitions in the fundamental structure of space-time itself. According to string theory, these cosmic strings were forged in the first moments after the Big Bang as the universe experienced rapid shifts in its fundamental state. They are like fractures in a frozen lake, delineating the boundaries where different regions of space crystallized in slightly different configurations as the cosmos cooled from a state of perfect symmetry. A cosmic string just 1 meter in length would have the mass of the entire Earth. Yet these objects are so thin they are effectively one-dimensional, possessing length but no discernible width or height. They occupy the very edge between being and non-being, matter and energy, a manifestation of pure mathematics and reality. The energy confined within a cosmic string is almost beyond belief. A string stretching from the Earth to the Moon would hold enough mass energy to sustain human civilization for trillions of years. This tremendous power is focused into a line so narrow it has no measurable thickness, making cosmic strings the ultimate embodiment of energy density. If cosmic strings were to move through space, they would generate ripples in space-time, producing gravitational waves that could potentially be picked up by our most sensitive detectors. These waves would possess a unique signature, distinct from those created by merging black holes or neutron stars, which could allow scientists to confirm the existence of these hypothetical structures. When two cosmic strings cross paths, they can form loops that oscillate like guitar strings plucked by the universe. Instead of generating sound, These vibrating loops create distortions in the fabric of reality, sending gravitational waves cascading outward at the speed of light. These cosmic string loops would gradually lose energy through this gravitational radiation, shrinking over time until they finally vanish. A loop the size of our solar system would radiate away its energy in just a few million years, disappearing in a final burst of space-time disturbance. Some physicists speculate that cosmic strings could serve as cosmic expressways, enabling faster-than-light travel through warped space. If 2 points were connected by a string, one could theoretically travel along it and arrive at the destination before light, taking the conventional route, making them the universe's ultimate shortcuts. Others believe cosmic strings might be gateways to extra dimensions concealed from our three-dimensional perception. The strings could be fundamental objects residing in a higher dimensional space, with only their one-dimensional signatures visible in our reality. These theoretical marvels remain confined to the equations of physics, awaiting either discovery or refutation by future observations. For billion light years from our world, a black hole the size of our solar system is firing a beam of particles that spans an entire galaxy. This jet of superheated plasma travels at 999% the speed of light, carrying enough power to energize 1 trillion stars while remaining perfectly focused over distances that defy human scale. Quasar jets originate in the chaotic environment around supermassive black holes, where space-time itself is a war zone between gravity and magnetism. As matter spirals toward its inevitable fate, it creates an accretion disk spinning at phenomenal speeds. Magnetic fields, amplified by the disk's rotation, get twisted into complex arrangements that store immense energy. These magnetic field lines function as cosmic particle accelerators, funneling material from the disk's inner regions into tight beams that shoot out from the black hole's poles. The very gravitational forces that should drag everything to its doom instead, through this magnetic catapult, launch some material back into space at relativistic velocities. The jets are so remarkably straight, they seem to have been drawn with a cosmic straightedge. They hold their narrow form over hundreds of thousands of light years, threading through space with a precision no human technology could ever replicate. The collimation is so flawless that jets observed with radio telescopes look like thin lines, even when viewed from billions of light years away. The particles within these jets possess energies millions of times greater than anything we can generate in our most powerful accelerators on Earth. Individual protons hurtle along the jet at speeds so close to that of light that their relativistic mass swells by thousands of times, transforming ordinary matter into cosmic projectiles of unbelievable force. When a quasar jet is aimed directly at Earth, we observe it as a blazer, and its light appears to fluctuate as the beam sweeps past us like a cosmic lighthouse. These blazers can change in brightness by hundreds of times in a matter of days or even hours, as turbulence within the jet creates bright knots of emission moving toward us at apparent speeds exceeding that of light. This superluminal motion is a trick of perspective, an illusion created by the geometry of observation when material moving at 99% light speed travels almost directly toward us. The effect underscores just how close to the ultimate cosmic speed limit these jets truly are. The most powerful quasar jets carry enough energy to heat entire galaxy clusters, inflating enormous bubbles in the surrounding gas that can last for hundreds of millions of years. These cosmic blowtorches can halt the formation of new stars across regions spanning millions of light years, effectively sterilizing vast volumes of the cosmos. Recent observations have spotted jets extending far beyond their host galaxies into the intergalactic medium, where they continue to travel for millions of years, carrying the imprint of black hole activity from ancient cosmic eras. In a binary star system 30 million light-years distant, a white dwarf star is siphoning material from its companion, like a celestial vampire drawing stellar lifeblood. For millennia, hydrogen gas has streamed from the larger star onto the compact remnant, accumulating layer by layer like snow on a peak. But this stellar accretion is nearing a critical point that will set off one of the most uniform explosions in the universe. White dwarfs are the dense cores remaining after sun-like stars use up their fuel and cast off their outer layers. These stellar relics pack the mass of our sun into a volume the size of Earth, creating matter so dense a teaspoon of it would weigh as much as an automobile. Their surfaces glow at tens of thousands of degrees, hot enough to incinerate any known substance. The stolen gas builds up on the white dwarf surface, where it is compressed by gravity into a thin shell of hydrogen that grows ever hotter and denser. The white dwarf acts as a cosmic pressure cooker, gradually heating this pilfered matter until nuclear fusion begins to ignite in its surface layers. When a white dwarf's mass reaches precisely 14 times that of our Sun, a catastrophe ensues. This critical mass, the Chandrasekhar limit, is the maximum weight that electron degeneracy pressure can withstand. Beyond this threshold, the star can no longer resist its own gravitational pull. The accumulated material detonates in a runaway thermonuclear blast that completely obliterates the star in seconds. The explosion spreads through the white dwarf like a flame front racing through cosmic dynamite, transforming carbon and oxygen into iron and nickel through explosive fusion. The star literally incinerates itself out of existence. This event is a Type Ia supernova, and it is one of the most consistently violent occurrences in the cosmos. Every Type Ia supernova releases nearly the exact same amount of energy because each one involves the same amount of material undergoing the same nuclear process. This cosmic consistency makes them ideal standard candles for measuring distances across billions of light years. The explosion shines with the brightness of 5 billion suns and is visible from galaxies billions of light years away. For several weeks, a single exploding white dwarf can outshine an entire galaxy of hundreds of billions of stars. Its brightness peaks rapidly before fading over months as radioactive elements forged in the blast decay and release their energy. This type of explosion synthesizes and disperses elements crucial for life across immense regions of space. The calcium in your skeleton, the iron in your blood, and the nickel in our currency were all created in the hearts of exploding white dwarfs. We are quite literally composed of stellar debris scattered by these cosmic cremations billions of years ago. The shock wave from a Type Ia supernova expands outward at thousands of miles per second, heating the surrounding gas to millions of degrees. The blast can spark new waves of star formation in nearby clouds, while simultaneously enriching them with the heavy elements required to form planets. Two city-sized objects spiral toward one another in the dark of space, locked in a gravitational death embrace that has endured for millions of years. They are neutron stars, the collapsed cores of massive stars, and their collision is about to unleash the most violent event in the local universe while creating elements more precious than any royal treasure. Each neutron star holds more mass than our Sun, crushed into a sphere just 12 miles in diameter. Their surfaces are composed of atomic nuclei packed so tightly that a single teaspoonful would weigh 6 billion tons on Earth. These are not conventional objects. They're the densest form of matter that can exist without collapsing into a black hole. As they orbit ever closer, the neutron stars deform one another through sheer gravitational might. Tidal forces stretch and compress these incredibly dense bodies like cosmic putty, generating friction that heats their surfaces to millions of degrees. The orbital dance quickens as they lose energy through the emission of gravitational waves. These gravitational waves carry away orbital energy at an accelerating rate, causing the neutron stars to spiral inward ever faster. The waves are ripples in space-time itself, stretching and compressing the fabric of reality as they propagate outward at light speed. Sophisticated detectors on Earth can measure these waves, even though they alter distances by less than 100,000th the width of a proton. In the final seconds before impact, the neutron stars are completing hundreds of orbits per second, whipping around each other faster than a helicopter's rotor. The gravitational waves they emit become so intense they carry away the energy equivalent of 3 solar masses in the last few moments before they touch, causing the death spiral to accelerate exponentially. When the neutron stars finally make contact, they produce a brief, intense flash of gamma rays followed by a longer-lasting explosion known as a kilonova. The collision is so cataclysmic it literally shakes the cosmos, sending gravitational wave signals that can be detected from billions of light-years away by instruments designed to measure the impossible. The merger forges elements heavier than iron through a process called rapid neutron capture. In the extreme conditions of the collision, atomic nuclei are showered with so many neutrons they can barely absorb them fast enough. This creates unstable, neutron-rich isotopes that decay into stable heavy elements, including gold, platinum, and uranium. A single neutron star merger can produce quantities of gold equivalent to the mass of several Earths, along with similar amounts of other precious metals. The collision ejects this stellar treasure at speeds approaching 1/3 the speed of light, seeding the surrounding space with materials that will eventually be incorporated into future generations of planets and asteroids. The impact ejects material in multiple waves moving at different speeds. The fastest debris generates the initial gamma-ray burst, while slower material forms expanding shells that glow from radioactive decay for weeks. This kilonova light is produced by billions of newly formed atomic nuclei undergoing radioactive decay, creating a fireball that shines with the light of hundreds of millions of suns. 138 billion years ago, everything that currently exists was compressed into a point smaller than a proton. All the matter and energy in the known universe, from the tiniest quantum particles to the most massive galaxy clusters, occupied a space of no dimension. This was the singularity of the Big Bang, the ultimate expression of cosmic power, the instant that existence itself ignited. At that primordial moment, the laws of physics as we know them ceased to apply. Temperature and density were infinite. Space and time were meaningless. The 4 fundamental forces that rule the modern universe were merged into a single, indescribably powerful interaction that commanded reality. In the first fraction of a second, a duration shorter than the time it takes light to traverse a proton, the universe expanded faster than light itself. This period, known as cosmic inflation, stretched space by a factor of trillions upon trillions in less than the blink of an eye. The universe did not explode into a pre-existing void, but rather created new space as it expanded, carrying matter and energy along with it. The temperature during these initial moments was so extreme that even the fundamental forces of nature could not exist as distinct entities. Gravity, electromagnetism, and the strong and weak nuclear forces were all indistinguishable aspects of a single superforce that has not existed since that first instant of creation. As the universe expanded and cooled, this cosmic unity shattered like glass, cooled too rapidly. The forces broke apart in a series of phase transitions that unleashed enormous energy and set the basic framework of physical law. First, gravity separated, followed by the strong force, and finally, electromagnetism diverged from the weak force. In the first minute after the Big Bang, the universe cooled sufficiently for the first atomic nuclei to form in a process called Big Bang nucleosynthesis. Protons and neutrons, recently condensed from cooling quarks, fused together in a cosmic crucible that created most of the hydrogen and helium we observe today. The energy density was so intense that matter and antimatter were constantly annihilating one another in flashes of pure energy. For 300,000 years after the initial event, the universe was opaque to light. Free electrons scattered photons so effectively that light could not travel far before being absorbed and re-emitted. The cosmos was a glowing fog, filled with energy but impossible to see through. Then came the cosmic dawn. Electrons and atomic nuclei finally combined to form the first neutral atoms, which allowed light to travel unimpeded for the first time. This cosmic clearing event produced the afterglow we still detect today as the cosmic microwave background radiation, a faint echo of creation that permeates every corner of the sky. The Big Bang was not an explosion in space, but rather an explosion of space itself. It created time along with matter, establishing the laws of physics that govern everything from quantum jitters to the formation of galaxies. No event before or since has matched its power to bring forth everything from nothing and establish the very foundations of existence. And yet, even this cosmic genesis may not be the ultimate limit of power in our universe. Beyond the realm of ordinary supernovae, something far more savage exists. When a star containing 50 times the mass of our Sun finally depletes its nuclear fuel, it doesn't just collapse and explode. It triggers a hypernova, a detonation so energetic it eclipses regular supernovae by a factor of 10 to 100, releasing the energy equivalent of billions of atomic bombs detonating every second for millions of years. These stellar behemoths are exceptionally rare, even on cosmic timescales. Only the most massive stars in the universe can create hypernovae, and they must be rotating rapidly at the moment of their demise. The combination of extreme mass and swift rotation produces conditions so violent that a normal stellar death cannot contain the impending fury. When the core of such a star collapses, it forms a black hole almost instantaneously. However, the star's rapid spin prevents a simple, symmetrical collapse. Instead, the infalling material forms an accretion disk around the newborn black hole, spinning so fast that it becomes a cosmic dynamo, generating magnetic fields of unimaginable intensity. These twisted magnetic field lines act like springs wound to their breaking point. When they finally snap and reconnect, they discharge jets of matter and energy outward at 999% the speed of light. These jets drill through the collapsing star like cosmic projectiles, carrying enough energy to power our Sun for billions of years. The jets burst through the star's outer layers and erupt into space, creating the gamma ray bursts we observe from billions of light years away. But the violence doesn't stop there. The shock wave from the jet's passage heats the star's interior to temperatures that surpass those in the cores of normal stars, setting off explosive nuclear burning throughout the stellar remnant. Layer after layer of the star explodes outward in a cascade of thermonuclear destruction. Carbon fuses into neon, neon into silicon, and silicon into iron, all in a matter of seconds. The energy released by these rapid fusion reactions amplifies the devastation, creating an explosion that can be seen from the edge of the observable universe. A single hypernova can forge more heavy elements than dozens of typical supernovae. The extreme conditions produce radioactive isotopes that decay over weeks and months, fueling an afterglow that persists long after the initial blast. These cosmic foundries create many of the elements essential for life, scattering them across vast regions of space. The most powerful hypernovae can disrupt star formation across entire galactic regions. Their shock waves compress nearby gas clouds, igniting new waves of stellar birth while simultaneously heating the surrounding medium to temperatures that inhibit further star formation for millions of years across hundreds of millions of light years. Two massive galaxy clusters hurtle toward each other at speeds of thousands of miles per second. Each cluster is home to thousands of galaxies, trillions of stars, and vast oceans of superheated gas that emit X-ray light. When these cosmic titans collide, they produce the most energetic events in the universe since the Big Bang. Galaxy clusters are the largest gravitationally bound structures in the cosmos. The Coma cluster alone hosts over 1,000 galaxies and has a total mass equivalent to 100 trillion suns. When clusters of this size collide, the energy released can surpass the combined output of all the stars in both clusters by factors of millions. The collision starts slowly on a cosmic timescale, with the clusters approaching each other over hundreds of millions of years. Dark matter, which constitutes most of each cluster's mass, feels only gravity and passes through the collision relatively undisturbed. But the hot gas that permeates the space between galaxies suffers a much different outcome. As the clusters merge, their gas clouds collide at velocities approaching 5,000 miles per second. The impact creates shock waves that heat the gas to temperatures exceeding 100 million degrees, hot enough to strip electrons from any atom. The resulting plasma radiates brilliantly in X-rays, creating some of the most luminous objects in the universe. These cosmic collisions can trigger the formation of radio halos that span millions of light years. Magnetic fields, stretched and amplified by the merger, accelerate electrons to nearly the speed of light, causing them to emit radio waves as they spiral around the field lines, resulting in a ghostly radio glow larger than entire galaxies. The most violent cluster collisions can create bow shocks that travel outward at thousands of kilometers per second. These cosmic sonic booms compress and heat the surrounding medium, forging structures visible across immense distances. The energy contained within these shocks is greater than the total energy output of billions of supernovae. During the collision, individual galaxies within the clusters undergo their own violent interactions. Tidal forces can rip stars from the outskirts of galaxies, creating long streamers of stellar debris that trace the cluster's gravitational ballet. Some galaxies may be entirely torn apart, their stars scattered into the growing cluster's halo. The collision can also set off massive bursts of star formation as gas clouds within galaxies are compressed by the encounter. These starbursts can boost a galaxy's star formation rate by hundreds of times, creating brilliant blue regions populated by newly formed massive stars destined to live fast and die young. Hidden within the quantum foam that underpins all of reality lurks a prospect so terrifying it could extinguish everything we know in an instant. The Higgs field, which endows all particles with mass, may not be in its lowest possible energy state. If this field were to suddenly collapse to its true minimum, it would spawn a bubble of annihilation expanding at the speed of light, rewriting the laws of physics and obliterating everything in its path. The Higgs field permeates every corner of space, existing even in the vacuum between atoms. Like a ball perched on a hilltop, this field might currently reside in what physicists term a false vacuum state. It appears stable, but it could potentially roll down to an even lower energy level, fundamentally altering the nature of reality. If vacuum decay were to begin anywhere in the cosmos, it would create an expanding sphere of true vacuum, moving outward at precisely the speed of light. Nothing could escape this cosmic wave of destruction, as no information or matter can travel faster than light. We would receive no warning of its approach until the moment it arrived. Inside this bubble of true vacuum, the fundamental constants of nature would be different. Particles might possess different masses or cease to exist altogether. Atoms as we understand them could not form. The strong nuclear force might be weaker, causing all atomic nuclei to disintegrate instantly. Chemistry and biology would become impossible. The energy difference between the false vacuum and the true vacuum would be unleashed as the bubble expanded. This energy could surpass the rest mass energy of all the matter in the universe, making vacuum decay more energetic than converting every proton, neutron, and electron into pure energy. The universe would be inundated with more power than all its stars and galaxies combined. Current calculations suggest our vacuum may indeed be metastable, balanced precariously on the brink of stability. High-energy events like cosmic ray impacts or black hole evaporation could potentially trigger the transition. Even quantum fluctuations might spontaneously nucleate a bubble of true vacuum in empty space. The terrifying nature of vacuum decay lies in its inevitability if the false vacuum state is real. Quantum mechanics guarantees that any metastable state will eventually decay, even if the probability is infinitesimally small. Over the vast timescales of cosmic history, even the most improbable events become certainties. Vacuum decay would be the ultimate cosmic reset, Everything that has ever been, every star, planet, and living organism, would be erased and replaced by a universe with entirely different physics. No trace of our current reality would survive, not even a memory that it had ever existed. Some theories propose that vacuum decay may have happened multiple times in our universe's past, with each transition creating new regions with different physical laws. We could be living in just one bubble among many, surrounded by realms where the rules of existence are utterly alien. In the initial moments after the Big Bang, when the universe was smaller than an atom and denser than a neutron star's core, minute fluctuations in density could have collapsed to form black holes more massive than mountains, yet smaller than atoms. These primordial black holes would wield gravitational fields so intense they would warp space and time on scales invisible to us. Unlike black holes created from collapsing stars, primordial black holes could have any mass. Some might weigh as little as a paperclip, while others could surpass the mass of our sun. The smallest would be quantum objects, where the bizarre principles of quantum mechanics collide with the absolute dominion of general relativity in ways we are only beginning to grasp. A primordial black hole with the mass of a mountain would be smaller than a proton, but possess a gravitational field millions of times stronger than anything we can generate. Space-time around such objects would be contorted into impossible geometries, creating regions where familiar notions of distance and duration lose all meaning. These microscopic terrors would rank among the most violent objects in the universe. According to Stephen Hawking's calculations, black holes emit radiation and slowly evaporate. The smaller the black hole, the faster it evaporates and the more ferociously it dies. A primordial black hole with the mass of a large asteroid would explode with the energy of millions of hydrogen bombs. The final moments of a small primordial black hole's existence would be unimaginably spectacular. As it shrinks to subatomic dimensions, its rate of evaporation would accelerate exponentially. In its last second, it would unleash more energy than our sun produces in a year, all from a point smaller than an atomic nucleus. If primordial black holes exist in significant numbers, they could solve one of cosmology's greatest puzzles, the nature of dark matter. These invisible objects would exert gravity without emitting light, perfectly matching the properties astronomers observe in dark matter throughout the cosmos. The hunt for primordial black holes has led scientists to investigate some of the most extreme environments in the universe. When these objects pass through stars, they would heat the stellar material and cause detectable changes in brightness. If they collide with neutron stars, they might trigger observable gravitational wave signals. Some primordial black holes may have grown over cosmic time by accreting matter and merging with other black holes. These entities could now be hiding in the dark voids between stars, unseen predators awaiting an encounter with matter they can consume. Their gravitational lensing effects might occasionally bend and magnify the light from distant stars. The most massive primordial black holes could have served as the seeds for the supermassive black holes we see at the centers of galaxies today. This would explain the mystery of how such enormous black holes could have formed so early in the universe's history, when conventional stellar evolution had barely begun. Before the universe was even 1 second old, space itself experienced the most violent expansion in cosmic history. In a period shorter than the time it takes light to cross a proton, the universe swelled from smaller than an atom to larger than a grapefruit. This process, known as cosmic inflation, represents the most powerful force ever unleashed, stretching space faster than the speed of light and setting the stage for everything that followed. During inflation, space expanded by a factor of at least 10 to the power of 26 in just 10 to the power of minus 35 seconds. To grasp this, imagine a single atom suddenly growing larger than our solar system in less time than it takes light to travel across that same atom. This expansion was so rapid it defies human comprehension. The driving force behind inflation was a quantum field called the inflaton, which filled all of space with an immense energy density. Unlike normal matter, this field had the strange property of creating more energy as space expanded, acting as a cosmic fuel that never depleted. The more the universe grew, the more energy became available to drive further expansion. Inflation resolved several fundamental puzzles that had baffled cosmologists for decades. Without inflation, the early universe would have been filled with exotic particles and topological defects that should still be visible today. The rapid expansion stretched these objects to sizes far larger than the observable universe, effectively hiding them beyond our cosmic horizon. The expansion during inflation was so extreme that regions of space initially in contact were stretched far beyond any possibility of communicating with each other. This explains why the cosmic microwave background radiation has a nearly uniform temperature in all directions, even though these regions could never have exchanged energy after the expansion began. Quantum fluctuations in the inflaton field during inflation were stretched to cosmic scales, creating the density variations that would later evolve into galaxies and galaxy clusters. These tiny ripples in the fabric of space-time became the seeds of all large-scale structure in the universe, from the smallest stars to the largest superclusters. The amount of energy involved in cosmic inflation was truly colossal. In a tiny fraction of a second, the inflaton field released more energy than has been produced by every star in the observable universe over the past 138 billion years. This energy was converted into creating new space and filling it with the matter and radiation we see today. When inflation finally ceased, the inflaton field decayed into ordinary matter and radiation, reheating the universe to temperatures exceeding 10 to the 28th degrees. This was hot enough to create and destroy particles at rates that would make the cores of the most massive stars seem frigid by comparison. Some theories propose that inflation did not happen just once, but is an eternal process that continues to generate new regions of spacetime beyond our observable universe. In this scenario, our entire cosmos might be just one bubble in an infinite multiverse where new universes are constantly being born through inflation. In the heart of a dying star spinning at 1,000 revolutions per second, magnetic fields 1 trillion times stronger than Earth's are about to unleash destruction beyond imagination. This is a magnetorotational supernova, with a combination of extreme rotation and magnetic power, creates explosions that dwarf even the mightiest gamma-ray bursts, forging magnetic fields so intense they could tear apart atomic nuclei from thousands of miles away. One of the most massive stars in the universe end their lives. Some possess magnetic fields comparable to those of magnetars. If such a star is also rotating rapidly when its core collapses, the conservation of angular momentum spins the collapse even faster, like a figure skater pulling in their arms during a pirouette. As the stellar core shrinks from the size of Earth to just 12 miles across, its rotation rate increases by millions of times. The magnetic field lines frozen into the collapsing plasma become twisted and amplified until they reach strengths approaching the theoretical limits of physics. These fields become so powerful they can influence the structure of spacetime itself. The magnetic pressure in these extreme fields exceeds the pressure inside atomic nuclei. Field lines stretched to the breaking point store enough energy to power our sun for billions of years. When these magnetic structures finally become unstable and reconnect, they release this stored energy in violent magnetic explosions that make solar flares seem like gentle breezes. The combination of rapid rotation and extreme magnetic fields creates a cosmic dynamo more powerful than anything else in the universe. Charged particles caught in these fields are accelerated to energies far exceeding anything achievable in our most advanced particle accelerators. Individual protons gain enough energy to split atomic nuclei through pure kinetic impact. These magnetational explosions can launch jets of magnetized plasma at velocities approaching the speed of light. Unlike the jets from ordinary gamma-ray bursts, these magnetically driven outflows maintain their focus across intergalactic distances, creating beams of destruction that could sterilize planets from millions of light years away. The magnetic fields generated during these explosions are so strong they affect the vacuum of space itself. At field strengths exceeding 10 to the 15th Gauss, the quantum vacuum becomes birefringent, splitting light into separate polarizations and creating optical effects that exist nowhere else in the universe. Space itself becomes a kind of cosmic crystal with directional properties. Matter exposed to these extreme magnetic fields experiences effects that seem impossible by everyday standards. Atoms become elongated into needle-like shapes aligned with the field. The chemical bonds that hold molecules together are twisted and distorted beyond recognition. Even the fundamental particles that make up atoms begin to behave in strange new ways. The energy released by a magnetational supernova can exceed that of a normal supernova by factors of hundreds. The explosion synthesizes exotic isotopes that cannot be created under any other conditions, forging elements that exist for mere seconds before decaying into more stable forms. These cosmic alchemical laboratories create materials that push the boundaries of nuclear physics. In the vast halos surrounding every galaxy, an invisible substance outweighs all the stars by a factor of 5 to 1. This dark matter feels gravity, but interacts with nothing else we understand, creating a shadow universe that shapes cosmic structure while remaining completely hidden from our eyes. But if dark matter particles ever encounter their antimatter twins, they could unleash explosions that make supernovae look like fireflies. Dark matter particles, if they are their own antiparticles, would annihilate completely when they collide, converting their entire mass into pure energy. According to Einstein's famous equation, a single kilogram of dark matter undergoing annihilation would release the same energy as 21 million tons of explosives, making it the most efficient energy source theoretically possible. In the dense cores of galaxy clusters, where dark matter concentrations reach their peak, these annihilation events could create cascades of high-energy particles and gamma rays. The energy released would exceed the combined output of all the stars in the cluster, creating radiation so intense it could be detected from billions of light-years away. Some theories suggest that dark matter particles could be much more massive than ordinary protons and neutrons, potentially containing the energy equivalent of hundreds or thousands of hydrogen atoms compressed into a single particle. When such massive particles annihilate, they would create particle showers of incredible energy, producing cascade reactions that generate exotic particles found nowhere else in nature. The annihilation process could create pairs of photons with energies millions of times greater than visible light. These gamma rays would carry the signature of dark matter destruction, providing a direct window into the properties of this mysterious substance. The most energetic annihilation events could produce photons with energies approaching the Planck scale, where quantum gravity effects become important. If dark matter annihilation occurs preferentially in high-density regions, it could create feedback effects that shape the distribution of matter on cosmic scales. The energy released could heat nearby gas, preventing it from collapsing to form new stars. Entire regions of galaxies might be sterilized by the radiation from dark matter annihilation in their central regions. In the extreme environment near black holes, where dark matter densities can reach extraordinary levels, annihilation rates could become so high that they contribute significantly to the total energy output. These events might create observable signatures in the form of high-energy neutrinos or gamma-ray flares that could reveal the presence of dark matter concentrations. Some theoretical models predict that dark matter annihilation could trigger chain reactions where the energy release creates conditions favorable for further annihilation events. These cascading annihilations could empty entire regions of space of their dark matter content, leaving behind cosmic voids filled with high-energy radiation. The search for dark matter annihilation signals has led astronomers to examine the most extreme environments in the universe. Galaxy centers, where dark matter densities peak, are prime targets for detecting the telltale gamma-ray signatures of annihilation. The absence of clear signals so far suggests that either dark matter does not self-annihilate or the process occurs much more rarely than initially predicted. Somewhere in the depths of space, protons are being accelerated to energies that dwarf anything we can achieve on Earth. These cosmic ray particles race through the galaxy at 999,999% the speed of light, carrying individual energies equivalent to a baseball thrown at 60 miles per hour, compressed into a single atomic nucleus. The cosmic accelerators that create these particles operate on scales and with efficiencies that make our most advanced technology seem primitive. The most energetic cosmic rays detected on Earth carry energies exceeding 10 to the 20th electron volts, more than 10 million times the energy achievable in the Large Hadron Collider. A single one of these particles contains enough energy to light a small bulb for a brief moment, all concentrated in an object smaller than a proton. When such particles strike Earth's atmosphere, they create cascades of secondary particles that can trigger detectors spread across thousands of square miles. The cosmic accelerators responsible for these extreme particles remain one of astrophysics' greatest mysteries. Supernova shock waves can accelerate particles to high energies, but they cannot explain the most extreme cosmic rays. The electric fields required to accelerate particles to such energies would need to extend across distances of millions of light years and maintain voltages exceeding 10 to the 20th volts. Active galactic nuclei powered by supermassive black holes represent the most likely cosmic accelerators. The magnetic fields near these objects can store enormous amounts of energy, releasing it in sudden bursts that accelerate particles to relativistic speeds. The jets launched by these black holes create natural particle accelerators millions of light years long, far exceeding any human-built machine. When cosmic ray particles travel through magnetic fields in space, they're deflected and scattered, making it nearly impossible to trace them back to their sources. Only the most energetic particles, those with energies exceeding 10 to the 19th electron volts, travel in nearly straight lines through galactic magnetic fields. These ultra-high energy particles provide our only direct probes of the most extreme acceleration processes in the universe. The interaction of cosmic rays with magnetic fields creates some of the most spectacular phenomena in astrophysics. When these particles spiral around field lines, they emit synchrotron radiation that glows across the electromagnetic spectrum. The radio emission from our galaxy is largely produced by cosmic ray electrons spiraling through the Milky Way's magnetic field. Cosmic ray acceleration can occur through multiple mechanisms, each operating on different scales and producing particles with different energy spectra. Shockwave acceleration occurs when particles repeatedly cross shock fronts, gaining energy with each crossing. Magnetic reconnection can accelerate particles impulsively when twisted field lines suddenly snap and reconfigure themselves. The most extreme cosmic ray events might involve entirely different acceleration mechanisms that we have not yet discovered. Some theories suggest that the decay of exotic particles left over from the Big Bang could produce cosmic rays with energies exceeding anything possible through conventional acceleration. These hypothetical particles could be relics of physics beyond the Standard Model. Cosmic ray interactions with gas and dust in space create secondary particles, including gamma rays, neutrinos, and positrons. These secondary products carry information about both the cosmic rays themselves and the environment through which they travel. The study of cosmic ray secondaries has revealed the composition and structure of the interstellar medium in ways impossible through direct observation. In the apparently empty space between atoms, between planets, and between stars, the quantum vacuum seethes with invisible activity. Virtual particles pop into existence and annihilate each other in time, so brief they exist below the threshold of direct observation. Yet these quantum fluctuations, operating on the smallest possible scales, contain enough energy to power the entire observable universe and may ultimately determine the fate of reality itself. The quantum vacuum is not truly empty, but filled with zero-point energy that exists even at absolute zero temperature. Every cubic centimeter of space contains virtual photons, electron-positron pairs, and countless other particle combinations that borrow energy from the vacuum and must pay it back before quantum mechanics notices the violation. This constant creation and destruction of virtual particles creates an energy density that, if it could be extracted, would exceed the mass energy of all matter in the universe. Calculations suggest that the energy density of quantum vacuum fluctuations should be 10 to the 120th times larger than the observed energy density of the universe. This enormous discrepancy, known as the cosmological constant problem, represents one of the greatest failures of theoretical physics. If these calculations were correct, space itself would be so energetically unstable that atoms could not exist. Yet quantum vacuum fluctuations do produce measurable effects that confirm their reality. The Casimir effect demonstrates that two metal plates placed very close together will be pushed toward each other by the pressure of virtual particles. The space between the plates excludes certain wavelengths of virtual photons, creating an imbalance that generates a tiny but detectable force. Virtual particles near the event horizons of black holes can become real through a process discovered by Stephen Hawking. One member of a virtual particle pair can fall into the black hole while the other escapes, causing the black hole to slowly evaporate. This Hawking radiation represents the conversion of vacuum energy into real particles, demonstrating the tremendous power contained within quantum fluctuations. In the early universe, quantum vacuum fluctuations were stretched to cosmic scales during the period of inflation. These microscopic energy variations became the seeds of all large-scale structure, growing under the influence of gravity to form the galaxies and galaxy clusters we observe today. Every star, planet, and living being owes its existence to quantum fluctuations that occurred when the universe was smaller than an atom. Some theories suggest that our entire universe originated from a quantum vacuum fluctuation, a brief deviation from nothingness that somehow became permanent. In this scenario, the Big Bang itself was not the beginning of time, but rather the moment when a virtual universe became real, borrowing energy from the quantum vacuum that it has been repaying ever since through cosmic expansion. The power contained within quantum vacuum fluctuations might be accessible through advanced technologies that could manipulate the structure of space-time itself. Theoretical proposals for extracting vacuum energy involve creating negative energy densities or manipulating the boundary conditions that determine which virtual particles can exist in a given region of space. If vacuum energy could be harnessed, it would provide an effectively unlimited source of power that exists everywhere in the universe. A device the size of a coffee cup could potentially extract enough energy to power human civilization for billions of years, making all other energy sources obsolete overnight. New universes are constantly being born as quantum fluctuations trigger inflation in regions of false vacuum, creating an ever-expanding tree of cosmic domains that stretches infinitely in all directions. Each universe within this multiverse could have completely different fundamental constants. In some universes, gravity might be stronger or weaker, changing the formation of stars and galaxies. In others, the electromagnetic force might have a different strength, making atoms impossible or creating matter with properties we cannot imagine. The strong nuclear force could be altered, preventing nuclear fusion or allowing elements that cannot exist in our reality. The total energy contained within an infinite multiverse would literally be infinite, making it the ultimate expression of cosmic power. Every possible configuration of matter and energy, every conceivable physical law, and every potential history would exist somewhere within this vast ensemble of realities. The power to create infinite universes with infinite diversity represents the absolute pinnacle of cosmic force. Some regions of the multiverse might contain universes that expand forever, while others collapse back on themselves in big crunches that mirror their Big Bang origins. Still others might oscillate between expansion and contraction, creating cyclic cosmologies that repeat endlessly. The variety of cosmic destinies within a multiverse would encompass every possibility allowed by mathematics and physics. In certain interpretations of quantum mechanics, the multiverse consists of all possible outcomes of quantum measurements existing simultaneously in parallel realities. Every time a quantum event occurs with multiple possible results, the universe splits into separate branches, each containing a different outcome. This quantum multiverse would be constantly growing as new possibilities are realized. The anthropic principle suggests that we observe our universe's particular combination of physical constants, because only this combination allows observers like us to exist. In a multiverse containing all possible combinations of physical laws, conscious beings would necessarily find themselves in universes capable of supporting consciousness, no matter how unlikely such universes might be. If communication between different universes were possible, it could provide access to unlimited knowledge and resources. Technologies developed in universes with different physics might be incomprehensible by our standards, but could offer solutions to problems we cannot even imagine. The exchange of information across the multiverse would represent the ultimate expansion of scientific knowledge. The ultimate fate of the multiverse might involve the consumption of false vacuum regions by expanding bubbles of true vacuum, creating a cosmic selection process where only the most stable vacuum states survive in the long term. This could lead to a final state where all of reality converges on a single set of physical laws, ending the infinite diversity of the multiverse. We have ventured from the subatomic realm to the boundless multiverse, observing forces that push the very boundaries of what reality can support. From the strong nuclear force that binds atoms, to the theoretical possibility of infinite universes being born and dying without end, we have witnessed power on every imaginable scale. The most astonishing truth we have uncovered is that the universe doesn't merely possess power, it is power. Every atom in your body is held together by forces beyond conception. Every star illuminating the cosmic night burns because nuclear interactions convert matter into pure energy. Every galaxy pirouettes through the void because gravity and dark energy wage their timeless war across billions of light years. But perhaps the most profound revelation is that we, as conscious entities, are not separate from these cosmic powers. We are their direct creations. The calcium in our skeletons was forged in stellar cataclysms. The iron in our veins was dispersed by dying stars. The gold in our rings was born when neutron stars collided in violent embraces that shook space-time itself. We are, quite literally, made of stardust, assembled by forces so immense they can create and obliterate entire worlds. Yet here we are, conscious beings able to reflect on our own cosmic ancestry. This may be proof that the universe's greatest power is not its capacity for destruction, but its ability to generate complexity, beauty, and ultimately, awareness. The cosmos has labored for 138 billion years to manifest the conditions for your existence. Every force we have investigated, from quantum jitters to galactic collisions, had a part in bringing about this moment, a moment in which you can grasp your role in the cosmic narrative. What is the most powerful thing in the universe? Maybe it is not a single force, but rather the cosmos's endless creativity, its capacity to transform simple hydrogen into stars, stars into heavy elements, elements into planets, and planets into a stage where life and consciousness can arise to ponder the very powers that gave them form. The next time you gaze at the night sky, remember that you are observing the perpetual struggle between cosmic forces that have sculpted everything you see. And remember that you, fashioned from stellar ash and quantum dreams, are not merely a spectator in this cosmic play. You are one of its supreme accomplishments. The universe's most formidable power may ultimately be its ability to know itself through beings like us. In understanding cosmic power, we become the universe awakening to its own magnificent potential.